In this lesson, we're going to explore how alternating current is going to be part of the A2 course. The thing that you need to understand about this chapter is that we're not going to go into the details of how a transformer works. We're only going to use the formulas. If you want to learn about transformers in detail, you'll have to check out the link in the description. That is regarding the O levels or IGCSE concept of transformers. That is what you have to do before if you are having trouble in understanding transformers. So in this lesson, I'm just going to go through the questions. So we understand the term period, frequency, peak value, and the alternating current voltage. Let's find them out over here. So we have also done this in gravitation. We've also done this in oscillations as well. That how to look at this equation. So the way you look at this is going to be that omega that is mentioned over here is actually equal to 2 pi f, and this f is what we know from waves is actually 1 by t. So f is the frequency of the signal of the AC voltage that is going to be given in the question, and this x is actually x naught, or you can say that this is actually the peak value of that function. Now, for example, considering in this example that we already have, let's change the values. Right now the peak value is 1, so this function would not have a value over here because 1 multiplied by anything becomes the function itself. So if, for example, the peak value of this function was, let's say, 325 volts, for the sake of voltage at least, then this function will turn out to be 325, then a sine of omega t, whatever omega may be. So if let's say that the frequency of the signal is given to you as 50 hertz, that is what the Pakistani standard is. If this is how it's given to you, then how are you going to write down this equation? You will write this down in this way, that 325 sine. Now replace this f in this 2 pi f. So this becomes 2 pi into 50 into t, which was part of the system which we were not dealing previously. So this equation finally becomes 325 sine of 100 by t. Now, what is the purpose of this equation? You're going to put in the values over here of your choice. Now, this time period could be anything. It could be anything from 0 up to infinity. That is your choice. So what will this function do for you? Exactly in mathematics, since this is a sine function, it will give you a value against time. Now, for the sake of understanding and trying this example, let's go through some examples. I've gone through this example before in simple harmonic motion as well. SHM video part 1. I've also explained that over there. If you want to go into detail, you can go check that video out as well. So how to visualize this? Now, this function actually, now make sure that your calculator is in radians, right? Now we know that the frequency of the signal was 50 hertz. So the time period, if you calculate by 1 by 50, is going to come out as 0.02, which I like to write down as 20 milliseconds because this is what's going to be. Now, if I put in the value of t of my choice from 0 to 20 milliseconds, I will see that my function of sine wave actually come into about. Okay. Now, to prove this, let's try to do this on a calculator, which you can do that on your own as well. Let me show you how to do this on the calculator. Now, for the sake of understanding, I'm removing this 360 and I'm going to mention that this is 20 milliseconds because I know that the sine function or my wave, at least, that has a frequency of 50 hertz will be completed in 20 milliseconds. And at the center, I will find 10 milliseconds. Over here, I will find 5 milliseconds. Over here, I will find 15 milliseconds, right? So let's see how the calculator behaves in this way. Be sure to make your calculators in radians mode before you do this. So just hold on for a second. Let me show you the calculator. So let me show you how to make that equation once more. I've done that in many videos again. So 325, the peak value into the function of sine into 100 pi t. So 100 shift pi, and I'm going to choose alpha x for the sake of understanding, or let's say I choose alpha a. Now this a is exactly the same variable that I have selected over here as t. Now I will put t, time of my choice, and I will see how this is going to behave. Let's see what it does on the standard values, which are 5 milliseconds, 10 milliseconds, 15 milliseconds, 20 milliseconds. Let's see what it does. So I press the calc button and I put in the value of 5 milliseconds. I should expect the maximum value or the peak value, which I do get. So over here, when we come at 5 milliseconds, I am getting the peak value, which is 325. Now, if I put something less than 5 milliseconds over here, or I put anything greater than 5 milliseconds, I will get an accordingly answer. So let's see if I put in at calc, I put something less than 5, which is 2 milliseconds, right? You see, we get 191, which means that if you come at this point, let's say, if you were at 2 milliseconds, the value that you're going to get is 191 volts. Okay, so, and let's try this 10 millisecond factor. Let's see whether we get a 0 or not. So let's try 10 milliseconds. You can notice that we got a 0, which we know that from the graph is crossing the 10 millisecond part. So there will be a 0 over here. Okay, so I hope we understand what the function of this equation is and what are we trying to do with it. So moving on to the next part is regarding understanding the equation. We have understood what this equation actually means. Sinusoidally simply means that we are dealing with a sine function. It could have been a cos function as well. No need to worry. The graph only starts from a different position, as we've already done in AS mathematics as well. So the functions and the ideas remain the same. Okay. Now, the third part requires the understanding of RMS value first. So I'm going to go to the RMS concept first, and then I'm going to come to point number 3 in order of understanding at least. So there is a problem with the AC power calculations. The problem is that when we are dealing with an AC supply, for example, and we have a resistive load, let's say, which is, let's say, combined like this. Now the AC electricity actually flows in both directions. Okay, the formulas that we've done in O levels and IGCSE is V is equal to IR and P equals to IV. These are formulas for DC power, right? These are exactly, or you can say similar to AC power as well. They will be similar to this one, but there is an issue. The issue is that in DC circuits, we assumed, and we already know that the voltage is constant. Over here, the voltage is changing at every instant, as we saw in this equation as well. So how to tackle this problem? So what problem will it introduce? So I'll have a graph of voltage and I'll have a graph of current. So at every single instant, I need to put the value of voltage in this equation. And at every single instant, I will be making a coordinate for the current through that resistor. So I'll have to see a graph of current as well. And then to find power, I need to find, or I need to specify at what time do I want to find the power. So because these graphs are actually dealing with time, right? So what time do I see the current and at what time do I see the voltage? So ideally for a resistor, we see those things at the same time. So let's say I see these values at this time. So I pick this value, I get them multiplied and I find the power, right? Now this calls for another problem. I can't do this at all times since the frequency of the current provided by, or the voltage provided by bulb is 50 Hertz. It is changing in 20 milliseconds. It's beyond the scope of human being, at least human reaction error. So how do we do that at all times? So this actually tells us the problem with AC calculation, that we can't do this. We cannot do this at all times. So we need to find a method which will make this simple for us and still give us the same answer as if we were doing them like this. Okay. So let's see what's actually happening. So let's say that this graph is for voltage and this graph is for current. Okay. For a resistive load, the graphs are exactly the same. At certain voltage, there will be certain current. At a certain voltage else, somewhere else, the graph is still going to come out as same. So what is the power graph going to look like? What will the graph of power look like? Now notice that in this complete section, the current and voltage are positive. So if I had multiplied current and voltage, I will get a positive answer for power. And if I go to the other side, the voltage is negative, the current is also negative. If I multiply for power as current into voltage, negative multiplied by negative, gives me a positive answer again. So this graph of power at least is going to go something like this, that for example, if this is the complete cycle in 360 degrees or at least 20 milliseconds, and this will be, let's say, 10 milliseconds when the current and voltage both are 0. So this graph is going to go something like this. Two curved peaks like this one, and this will be your maximum power or P max. Right? And where do we find this? When the voltage was maximum and when the current was maximum. Similarly, when you go to the negative side and you go to the negative side of current, you get P max again. But why is this positive? Because both were negative. So multiplying two negative numbers gives you the positive answer again. So power's graph will never go to the negative side for a resistive load. It is always going to stay on the positive side. Again, I bring you back to this problem that this is not feasible for us to do at all times. We cannot look at time and we cannot look at power. We cannot look at voltage. We cannot look at current at all times. This is the problem with AC calculations. Although when you go to higher levels, when you go to engineering, when you go to science fields, you'll be doing this, the instantaneous power concept as well. But for A levels at least, we're going to limit ourselves to something that is going to make life easy. So that something that is going to make it easy for us is known as the concept of RMS. which means root mean square. So ideally speaking, what we're trying to do in this lesson, or at least in physics, the mathematics of it is not a part of the course. I will show you a slide in which you can explore this more if you've done AS mathematics or A2 mathematics, in which you've learned integration. Then you can most definitely go through this, but at least in A-level physics, we are not required to do the proof. So what we are trying to do, this is the solution for RMS, root mean square calculations. So you can pause the video and you can discuss this with your teacher of mathematics, at least of integration, if you want to explore this further, right? So what is the end product of this solution? What is the end result? So what we ideally want to do is that we want to convert this graph, which has multiple positive and negative peaks, into something that is going to have a constant value. This is what we want. Okay. Now, how do we do that mathematically speaking? So what we have done is that we take this sine function, at least. Let's say this is a sine function. Okay. So let's say this is sine theta function. So what we do is we take a square of this value so that even the negative part of the sine function becomes a positive part. You can see that over here, although we know that we have taken a square. So if this was 2, this would become 4, as you can see that over here as well. So we have in some sense lost the true value because the true value was 2. But no worries, we'll get to that later. So what we do first, we take the square of the function. That calls for this. When we speak root mean square, that deals with the square part of the function, because this is the first step that we followed. So we take the square so that the whole function becomes positive. Now notice that even this negative 2 square will become positive 4, which is why I see over here. So this is the positive peak, this is the negative peaks square. Then what I do to normalize it back again, because I took the square, so I'm going to take the under root of this whole function. So this covers the root part of this RMS value, or of this RMS word. I've taken the under root again so that I can compensate for this square that I took at the very beginning. Now the values have come back to the original value because the peak became 4. Now I take the under root, it becomes 2. Now the negative peak, effectively what has done is become positive. It has come to this side by taking the square and then reverse engineering it by taking an under root so that it becomes positive again. So now the negative value has become positive. Now we can calculate our values with less worry, at least. Okay. Now again, this serves a problem. I can't do this at every instant in time. It is not feasible for me to pick out values like this. We want something to do with average value. We want something to do with mean. So the mean part of this calculation is taken care of, visually speaking, at least. Mathematically, this is what's actually happening over here. The whole function, by integration, when we find the total area, we're going to spread it out, we're going to spread it down in the same time, in the same area, with respect to time, right? So you can see this 1 over pi function, which is actually 1 over t. We know that we're dealing with pi, at least, which is, we know that is equal to 180 degrees. So we're just finding the area of half of it because we know that the rest of this is going to be twice of that. So again, I urge you to discuss this with your mathematics teacher who teaches you integration. You can get to this later as well. So I want this whole area, whichever is being represented over here, to be converted into something that is going to be, or that is going to have a constant value like this, at least a constant value. So visually speaking, what we've done is we've adjusted all these areas in these tiny spaces, and these peaks have also been adjusted on the tiny spaces. So most definitely this maximum peak is going to come down because we're filling this area by cutting off this area and putting it over here. Again, this is simple geometry, visual solution of the problem, not mathematical, that what we have actually done. So what this does for us, by taking the mean, by taking the average of all these values, then dividing with that time scale over which it is being spread out, I've converted this to an average value, which now looks like a DC value. Notice what we have done. We came from an AC side, we came from an AC solution, we started from an AC point, and we have effectively converted our signal to a DC value. Now this enables me to use V equals to IR and P equals to IV freely, as much as I want to do. because now the time is not a problem for me, because I know that whatever time I'm going to check these values, it's going to remain the same. This is the significance of RMS concept. Why are we doing this? We are doing this for convenience. We're doing this for ease. So let's see how those formulas actually turn out to be. Now, the formula for current and voltage is V peak voltage, if divided with under root 2, gives you an answer of voltage RMS. So what you do effectively is you choose the peak value. Let's say this was 2, for example, over here, this is 2. So I put in over here 2 and then divide this with under root 2. This will give you an answer of 1.4, which is somewhere over here, which is where the line is stationary at this point. You can try this over again, right? So now I don't have to worry about this sign value changing at all times. I can take this as 1.4 or the average value as peak divided by under root 2, and then I can solve questions. Same thing applies for the current as well, that RMS current is actually going to be equal to the peak current, the maximum current from the graph, and divide this by under root 2. So then you get an average value of current. Now I'm going to change the formulas for power that we have already done in O-levels and IGCSE. P is equal to IV. We have done I square R. We have done V square over R, right? So if we were dealing with peak power, let's say we were dealing with V peak and I peak, for example, then the peak power is actually going to come out something like this, that I'm going to replace peak power or peak values with their RMS values, for the sake of example, at least, okay? Or we can start with simple power, that's it. So I divide this RMS, okay? So I deal with, let's say, peak power, V peak divided by under root 2, because I'm dealing with maximum power, the peak power, multiplied by the I peak current divided by under root 2. What is this formula? This is IV. Deliberately I'm taking the peak values, so to find out the relationship between the peak power delivery and the RMS, or the average power delivery. What's actually the relationship between them? So I realize that this under root 2 multiplied by this under root 2, I get the answer of V peak multiplied by I peak divided by 2, which comes out as P max divided by 2. Okay, so if I am taking the average values, let's say over here, if I was dealing with RMS values, so I will take the VRMS, which is a replacement of this, and I will take the IRMS, which is a replacement of this, and I get to this equation that my maximum power divided by 2 is actually my RMS power. So let's simplify this. What does this mean? It means that if I had the current and voltage peak values over here, if I had the peak value of current and voltage, I peak, what I can do is I can find the maximum power by multiplying this I peak multiplied by V peak, or maximum value, right? This will give me the maximum power delivered, but at a single instant. Notice that this is only happening at one instant in time. This is not happening continuously. This is actually just one time when the current and voltage have the highest value. Do they have that value at all other times? No, they don't. So the power is actually decreasing, or you can say it's less at other instants in time. So my peak power or maximum power, if divided by 2, becomes equal to my RMS power or the average power. What is the significance of this equation? It only tells you that if these graphs are given to you, then you can use the peak values, find out the maximum power, divide this by 2, and you will get RMS power straight away. Instead of doing this, this is a shortcut, right? What convenience is in this? Because what would you have to do other way? If you wanted to find the RMS power, then you'll have to divide this peak value of current with under root 2, then pick this value of peak, and then divide this by under root 2, so that this becomes RMS, this also becomes RMS. Then you multiply them together to find out the power RMS, right? So it's a longer process. This one is a quicker process. That if he asks you in the question, what is the RMS power, you can use this formula as well. Find the maximum peak power at peak values, divide that by 2, you will get RMS power. We will solve a question like this in this video as well. So let's go back to the syllabus and see if we have covered all the points. You see, recall the fact that mean power is half the maximum power. We've just discussed that right now. And we understand how to RMS the values respectively as well. And what was the purpose of RMS? So that we can get rid of this negative sign in the graph. Negative becomes positive. Then we take the under root, so everything becomes positive. Now we take the average and spread out the area over a constant value for the same time, so that we can get a fixed value, so that we don't have to worry about considering time in all those equations again and again. So let's move to this transformers. Now, transformer is a part of your course. I'm repeating the statement again. You have to watch the video of O levels if you want to understand how this transformer actually works. Okay, this is induction process or electromagnetic induction primarily. But let's move to the formulas. You can look at the diagram of the transformer, number of turns, current, and voltage. So the formulas actually come out as number of turns of primary divided by secondary is equal to voltage of primary divided by voltage of secondary equals to current of secondary divided by current of primary. And we also know that for an ideal transformer, the input power is equal to the output power, right? So what is the job of the transformer? To change the level of voltages. By looking at the coils, I can see that the primary has higher number of turns and the secondary has less number of coils, less number of turns. So its voltage will be less in comparison to the primary side. So this is basically a step down transformer. Just a tidbit from the O levels video, right? Okay, now this is the core of the transformer. It is generally made out of soft iron so that we can deliberately change magnetic fields again and again easily, so that it provides less resistance to the changing magnetic field. Now this is what is going to be a part of A levels concept at least. So what type of losses do we have in a transformer? We have two losses, the copper losses or ohmic losses. What are these losses? Where do you find them? These are basically I square R losses, and we know that power is equal to I square R. Where is this taking place? So this is taking place on both sides. You see, if you demand current from the secondary side or you inject current into the primary side, these coils that you have made on the primary or on the secondary side, they have a resistance. These are wires. These are very long wires. They will have a resistance. So when the current starts flowing in these coils, there will be some resistance of these wires, which is going to lose or which is going to drain power from the actual source that you've provided. So the first loss or first cause of loss is actually the copper loss or the power losses in the windings, which we call in layman terms, or you can say in the coil as heat. So the transformer heats up because of these losses in the wires. There is no way we can reduce this, but we know that it exists. Okay, so then we move towards iron and core losses. Now this is a bit new. This is a new concept in your syllabus. So what is iron core losses? You see, when you are actually changing the voltage in the primary coil, when you're changing the current in the primary coil, it causes the magnetic flux in this core to change. So sometimes the dipoles will be organized in this way, sometimes they will be organized in this way because of the magnetic field that you've provided due to this primary current. So when this magnetic dipole has to change from this position to this position, then back to this position, this is going to require energy. This is going to require some effort from the current that you are injecting into the primary coil. So this domain change losses is actually the hysteresis loss. So when the magnetic domains, and if you want to learn what are magnetic domains, please watch the O levels video. So when the magnetic domains have to change their orientation again and again from this side to this side to provide changing magnetic flux, so an induced EMF according to Faraday's law can be introduced in the secondary coil. This is going to cause some loss of energy as well, because you will not get it. You will not get this on the output. This will actually be used in the process. And then we have eddy current losses. This is a very interesting concept, and one of, you can say, key points in the transformer that are generally ignored. You see, what are eddy currents? What are the eddy currents in the core? So basically what's actually happening is, since we know that this is made out of iron, we know iron is a conductor, right? And from Faraday law, we know that if any conductor experiencing a changing magnetic field, it will experience induced EMF. Very basic O levels definition of Faraday law, right? So let's make it even more simple. If a conductor experiences changing magnetic field, it will experience voltage, and wherever there is voltage, there is going to be some current according to Ohm's law in that resistance, of course. So over here, what's actually happening is that this magnetic flux is flowing through this core. The magnetic fields are actually changing, the dipoles are actually changing at all times, as in the hysteresis laws, right? So what's going to happen? This is an iron core. When iron, a conductor, experiences changing magnetic field, there is going to be an induced EMF in this core as well. So for the sake of example, let's say that one terminal becomes positive because of the induced EMF voltage, and one terminal becomes negative. What's going to happen? It will cause a flow of current in the core, and this is eddy current. These are eddy currents. The core was not supposed to do this, but it is doing that because it has nothing, it has no power over it, it has no control over it. Because you are providing changing magnetic field to a conductor, it will produce induced EMF, and that EMF, that voltage, will cause a certain current in that resistor. And of course, iron is a conductor, but of course it will have some resistance as well. 1 ohms, 2 ohms, 3 ohms, we don't know. It will have a resistance. Now, what do these eddy currents do? And most definitely, they are going to change their direction, because we know that we are working with an AC supply to constantly change the magnetic field. So sometimes the magnetic field is like this, sometimes it's going to be like this. So sometimes the current is also going to be like this, and sometimes the current is going to be the opposite direction, just like a sine wave. So eddy currents will not stop moving, or will not be stopped from at least generating. So what do these eddy currents do? What's the problem with that? So eddy currents, we know from electromagnetism and magnetic induction that if, let's say, we have a wire and the wire has a current, we know that it has a magnetic field around it in a circular fashion, which we used to do in O levels as dot and cross model. Something is out of the page and this is into the page, and there will be a circular magnetic field around these conducting wires. So we know that a current carrying coil has a magnetic field around it. So what's going to happen because of this eddy current in this core? This eddy current that is flowing in the core will produce its own circular magnetic field of the iron core, which you didn't do. You did not intended this to happen, but it is happening nonetheless due to eddy currents, right? So this magnetic field opposes the magnetic field being produced by the primary coil. The secondary coil has nothing to do with it. It is on the receiving end. It's waiting for the change in magnetic field so that it can induce EMF. So it has nothing to do with this. Now this eddy current, which has been caused because of the changing flux in the core, is going to start opposing the magnetic field produced by the primary coil, which was used to produce this magnetic flux. So it's like a chain reaction. You provided the AC current. That AC current changes the magnetic field so that secondary EMF can be induced due to Faraday law. But this also induces EMF in the core because it's made out of iron. It's a conductor. That current, when flows, produces a magnetic field in the core at all points. Let's say over here, over here, over here, over here. This magnetic field is going to start opposing the magnetic field produced by the primary coil. Or in depth, in great detail, this is going to start opposing the magnetic flux itself, which is actually flowing through the core. So what is it going to do? It is going to produce losses. It's going to reduce the efficiency of the transformer. It is going to drain the transformer of the magnetic field because it is opposing the magnetic field produced by the primary coil. So that is also one of the causes of loss in a transformer. Now, how do you avoid this? We can't eliminate this completely, but how to avoid this? You see, we can't stop this induced EMF of eddy current forming in the core. We can't stop this, but we can reduce this. How do we reduce this? According to Ohm's law, we understand that voltage is equal to IR. We can't reduce the voltage. The induced EMF can't be reduced. So what we want to do is reduce the eddy current, which is I. So let's bring R over there. So this is V over R equals to I. What do? We can't control voltage because we need that magnetic induction. We can't do this. So what we do, we deliberately increase the resistance of the iron core so that the eddy current can reduce and its opposition to the magnetic field will reduce. Now, how do we do that? How do we reduce the resistance of the core? You see, we understand from O levels that the resistance of any conductor is inversely proportional to cross-section area. Where does this come from? You might remember rho L over A, resistance of a conductor. So resistance and cross-section area are inversely related. If I increase the cross-section area, resistance decreases because the electrons have a wider path to flow through. They will feel less resistance. So I want to decrease the cross-section area so that resistance deliberately increases so that current will decrease. How to reduce the cross-section area? You see, right now the cross-section area of this core is at least this much. It's a very high cross-sectional area in terms of 3 dimension. So what do? I am going to reduce the cross-section area by creating slices of this iron core. I will deliberately divide this core into slices of iron sheets. And then I'm going to place plastic sheets between them and sandwich plastic sheets between them. Why? So that one sheet is isolated from another. Now, what's happened at this point? You see, this one sheet, how meter thick or thin it may be, does not have the same cross-sectional area as much as the full core's cross-section area. So I have reduced the cross-section area by making them into thin slices, increasing the resistance so that I had no control over the voltage induced EMF, but I have control over the resistance, so the eddy currents will reduce and the transformer losses will reduce and the efficiency of the system will improve. So I understand that I hope that we understand what are the power losses or the source of power losses in a transformer. This is not covered in O levels. This is primarily covered in A levels, right? So we understand the eddy current losses, the hysteresis losses. We understand the copper or heating losses. Okay. And all of these three losses generate heat in the transformer, one way or the other. Transmission at high voltages is also a part of O levels. You'll have to go and watch that video. But for the sake of understanding, I'm just going to give you a brief idea. You see, we are transmitting current and power. Sorry, not current and power. We are transmitting power at high voltage. Why are we doing that? When, let's say, the electricity is generated at Wabda station, for example, let's say for the sake of example, they're producing at 25,000 volts and they want to provide, let's say, 5,000 megawatts of power to the whole country for the sake of understanding. When they transmit that over long distances using poles and wires, there is a significant resistance of these wires that is going to account for the power losses, the I square power losses to be precise, right? So we want to minimize them. So what we do, we deliberately use transformers and increase the voltage to a very high value. Let's say that we've increased the value to approximately, not like 25, let's say 115,000 volts, which is much greater than this. Why are we doing this? Because if I look at the formula for power, if I increase the voltage, I get to reduce the current and the power remains same because I'm multiplying those two numbers. So if voltage becomes a larger value, current becomes a smaller value, even though current is now smaller. If I multiply them together, I will get the same power that I want to transmit. So I have deliberately increased the voltage from 25,000 to 150,000 so that this current in the lines decreases. And then the end user will have its own transformer like we have on outside our houses to change the level of voltage according to my needs. I will change voltage according to my needs at the receiving end. So Wabda or the source or your electrical source is going to increase the voltage deliberately to reduce the current. You receive very high voltage, but you will use a transformer to step it down so that it becomes safe for your usage in your house. For more details, you'll have to watch the video of O levels transformer. Let's try to solve this question. Again, you will see that he will ask questions from O levels as well. Be advised. Why the core is made out of transformer and why are we doing that? Okay, so it is easy to magnetize and demagnetize, and we want to reduce the eddy current losses. Sorry, that is the only process of this part. Okay, then we have why an electromotive force is not induced at the output when a constant. You see, why can't we use a transformer with a DC source? Because a DC source provides a constant voltage, constant current. We can't use it in our transformer. Why can't we use that? Because if the current is not changing, the magnetic flux will not change. If the magnetic flux is not changing, then there is no change in magnetic field. If the magnetic field is not changing, according to Faraday's law, there will be no induced EMF. So DC does not provide changing flux. Hence, no EMF will be induced. Then what's the purpose of using a transformer if we can't change the level of voltages? Okay, so let's look at this question. He tells you that the primary peak value is 150 volts and 1200 turns in the primary. We have the secondary voltage peak value is approximately 52 volts. You can pause the video, count the boxes. And the frequency is also given to us. So he says, calculate the number of turns of the secondary coil. So very simply put at this point, what we can do over here is use the formula for NP over NS equals to VP over VS, right? So what are the number of primary turns? These are given in the question as 1200. The number of secondary turns, this is what we have to find out. The primary voltage at peak value was given to us as 150. Okay, so this is 150 and this peak value is 52. So when you find out X, now notice you could have solved this question with RMS values as well. But if you're dealing with RMS, then if you take one RMS, then you have to take the other voltage as RMS as well. So I'm only dealing with this in terms of peak voltages or peak values. So this comes out as the number of turns. Just a moment. Let me calculate this. So this comes out as 416 turns precisely. So this is going to be 416 turns. State one time when the magnetic flux linkage secondary coil is maximum. He asks you at what time the magnetic flux linkage will be maximum. So we go back to the graph. At this point, we see that the voltage is changing, right, at all times. You can see over here that the peak value that we almost approach is happening at somewhat less than 5 milliseconds. So you'll have to count the number of seconds at that point. Now, notice that at this point when the voltage is maximum, that means that the flux has already reached its maximum value. The maximum change we observe, or the maximum changing voltage we observe, is actually at this location, is actually at the gradient function over here. So we see that at 0, that has a maximum gradient. At approximately 7.5, it has a maximum gradient. At approximately 15, it has a maximum gradient. So most definitely, if the EMF is changing very drastically in these regions, then the flux or the change in flux would have happened at a maximum time. Okay, so these times could have been at the very beginning. This could have been at 7.5. This could have been at 15. This could have been at 22.5. You see, maximum flux linkage can only take place when there is the change of magnetic flux or the change of EMF is at its maximum. The change, we're talking about the change, because we know that the induced EMF depends on the change of magnetic flux with respect to time. So we are looking at the gradient of the EMF graph if you want to find the maximum magnetic field change at a given time instant. Okay, so let's move on to the next question. He said that a resistor is connected between the output terminal secondary coil. Okay, fine. So what's actually happening at the output coil? So this is the, let's say this is the output coil of the transformer. This has 416 turns. This has a peak voltage of 52 volts. And the resistor is connected with has a mean power. Notice that this is a word that's going to cause trouble. Mean power across the resistor has come out to be 1.2 watts. Now we know that the peak power, if divided by 2, gives me the average power or the mean power or the RMS power that we've just done in this lesson. So he tells you calculate the resistance of this resistor. So what you could have done is do it in two ways. Okay, so if you are dealing, let's say, with the RMS value, then we can simply use the formula that is P RMS equals to V RMS whole square divided by the resistance R. And I have taken this formula for P is equal to V square over R. And of course, if we are dealing with RMS, then we will be using RMS voltage. So since this mean power is the RMS or an alternate term for RMS, if I'm using 1.2 at this point, that will be 1.2 equals to, then I have to use the mean power. So this is the peak power, 52 volts peak voltage. If I want to find out the RMS voltage, then that would be 52 divided by under root 2, which I've already done in the RMS concept. This comes out as 36.8 voltage at RMS value, of course, average value. So 36.8 whole square divided by R, take that over there, bring that over here. You get R is equal to 1128 ohms, which can be simplified as at least 1100 ohms, 1100 ohms, because we have to write down answers in two significant figures. Now this is a problematic situation. He says to sketch out the graph of power. Now when we go back to the voltage graph, we understand that the current graph is also going to follow exactly the same behavior at this point. Notice that if we wanted to find the peak value of current, the peak current, how would we have done this? We know the resistance is fixed. So we would have used V equals to IR. The peak voltage is 52. Current we don't know. Resistance is 1100. And you can take 1128 for precise calculations. So the current comes out as 52 divided by 1100. The current comes out as 47 milliamperes. So this is 47 milliamperes. So the peak current, peak current comes out as 47 milliamperes. But are we dealing with the peak currents? Are we dealing with these answers? I could have found the IRMS of this as well by dividing this number with under root 2. This comes out as 33 milliamperes. Okay, so this comes out 33 milliamperes. Notice what will happen at this point. So we have RMS voltage, we have RMS current. Let's find out the power of RMS mean value. This should come out as 1.2. Okay, let's try that. So we have 36.8 volts multiplied by 33 milliamperes. Let's see what happens. You can pause the video, try this on your own. 36.8 multiplied by 33 e minus 3. I'm just doing this as an average, right? So you can take higher decimal value. So 1.214 watts, which was given in the question. This is the average power, but this is not the average power graph. This is actually the instantaneous power graph because we are dealing with time. So when I go back, I see that where is it going to be 0? So at these instants, 7.5, 15 and 22.5, I see the voltage is 0. So if the voltage is 0, the current will also be 0. So let's first put out these coordinates. So at 0, the coordinate is 0, 7.5, the power is 0, 15, the power is 0, 22.5, the power is 0. And notice how the power is actually happening. This is what we discussed at the very beginning of the lesson, that no matter how you deal with power, this is the graph of the power that it's going to look like. So this is my peak power by using peak value of voltage and peak value of current. And this is my RMS power. And the RMS power would be a bit less than that. So this is RMS power. Let's find out the peak power by multiplying peak voltage 52 and multiplying peak current, which is 47 milliamperes. And you'll notice something that we've already done. So 52 multiplied by, I'm doing this extensively so you can understand the concept properly. Nice. This comes out as 2.4 watts. So let's round this off to 1.2 watts. And this is 2.4 watts. What did I teach you in the previous, in this previous part of the video? What was that? It was that the peak voltage, peak power, divided by 2 gives me the RMS power. See, the peak power is 2.4. If I divide this by 2, I get 1.2, which is the average power. So, of course, this is not required by this part. I did this to explain this to you, how to visualize this. Now, this graph is actually instantaneous power in terms of the peak. So the peak power is also required and all the rest of the powers are also required. But we can't do that because the question is for 3 marks and we can't waste a lot of time over here. So what's actually happening, that when the voltage gets its peak value of 52, my current also has a peak value of 47 milliamperes. Of course, I can't show this over here because the scale is different. So in short, what I'm going to do, I'm going to choose 2.4 as my max power coordinate, which I discussed at this point, right? So now you might be thinking, why do I need to do so much working over here? Do I need to do so much work? No, you don't. You simply had to take this 1.2 and multiply this with 2 because you need to remember that there's a relationship of 2 times between them, peak and RMS. Now, if you figured out the RMS value is 1.2 watts, the peak value would be 2.4 watts. So in the middle of this time section, somewhere along here, you will find the peak power coordinate. So somewhere along here in the middle, somewhere along here in the middle. And this graph is going to look something like this. Peak power, then again peak power, and then again peak power, ultimately ending the cycle. So this is my 2.4 watts peak power, and if I was dealing with an average power, let's say, it would have been at 1.2 watts at a constant value like this. It would have been a constant area like this. So what have the relationship that we found, that the peak power, if known, divided by 2 gives me the average power. But in this case, I knew the average power, so I take the 2 over there. So 1.2 multiplied by 2 gives me the peak power 2.4, which I will use to make this graph at every single instant in time.